talk will be given by Chandan Dasgupta.
Okay, so I begin by thanking the organizers for organizing this very nice meeting, and also, of course, for the opportunity to present some of our work. I'll be talking about some work that I have been doing in collaboration with several people. Smarajit was my ex-student who is now at TCIS Hyderabad. The present student, Shumilan, also was an ex-student who is now at Weizmann, and of course, collaborating with Shrikant for quite some time. So here is a brief outline. I mean, first I would like to basically give you some motivation for why we did what we did, and then quickly, this is going to be the main thing. What we have found is that there is a growing length scale associated with short-time relaxation in glass-forming liquids. So, and this was done by doing finite-size scaling. So, spend about most of the time here, and then I'll try to relate the results that we see for the short-time relaxation to some aspects of long time or alpha relaxation, the same glass-forming liquids, and then conclusions. So, very quickly, since this is the first one, this first talk I think in this meeting on the glass transition. So it's, this is sort of a mandatory slide whenever one talks about glass transition. The basic issue is that if you look at glass-forming liquids and if you are decreasing temperature, then the dynamics becomes very, very slow. In particular, if you look at, for example, the viscosity changes by maybe 14 orders of magnitude over a temperature range that spans maybe 50 degrees or something like that. So this is growth of relaxation times or viscosities in this case, I mean, more or less and the same thing. As you can see here, if you plot as a function of 1 over the temperature, the log of the viscosity, then we'll be looking at liquids which sort of behave like this, very nonlinear. So it is not Arrhenius, it's Super-Arthenius. And the basic problem, of course, is to try to understand why the dynamics is slowing down so much, why the viscosity is growing so rapidly, and so on and so forth. So that's, of course, one aspect. But another thing that I will be interested in this talk today is basically that if I now look at a supercooled liquid and look at, let's say, how density fluctuations relax in time. So there, of course, one looks at density autocorrelation function. And this relaxation is not simple. It is not non-debye. It's not exponential relaxation. There are several regimes of relaxation. And in particular, for this talk today, I'd like to distinguish between short-time decay, which we'll call beta relaxation, and I'll show you what that means actually, and long-time decay, which we'll call alpha relaxation. And the behavior of this function in the two regimes actually are quite different. So that is illustrated in the picture taken from a book by well-known people in this field. So here we are looking at this autocorrelation function and how it decays as a function of time. Initially, there is some microscopic regime which one is not interested very much. But then the important thing is that this decays into some kind of a plateau. And the behavior in this region, in the plateau region, is what I'll call beta relaxation, the short-time relaxation. And eventually, at much longer times, the function eventually will decay from this plateau, and that is the alpha relaxation time. These are not very well defined. I mean, as you can see here, the beta and the alpha are somewhat overlapping with each other and so on. But it is clear that the behavior at relatively short times is quite different from the behavior that you see at much longer times. And most of the studies of glassy behavior concentrate on this alpha relaxation regime. But today I'm going to talk about what happens here and try to relate what happens at this short-time regime to what actually sees in the long-time regime. So there actually, of course, when people, I mean, this has been known for a long time, and there have been some sort of quote-unquote theories of this beta relaxation, and the general picture that people used to sort of suggest is that when I look at a particular particle in the liquid, it's sort of course, surrounded by some kind of a cage formed by its neighbors, and the particle basically rattles around in this cage, and that is why the correlation function doesn't decay as a function of time. So this is sort of the caging regime, and then eventually the cage, of course, is also formed by mobile particles. The cage will break, and this particle will eventually go out, and this part is the sort of going from one cage to another or subsequent longer time dynamics. So this has been the general picture. So what we'd like to find out is to what extent this picture actually works for real systems, and whether one can actually find something which is a little beyond this. This is a very, very local in space picture. So the question is whether there is some long-range correlations also in the beta process. So this brings us to the notion of length scales, and again, don't want to go into too many details, but there have been a lot of investigation over the last 10 years or so on finding length scales that in some sense can explain, growing length scales that can in some sense explain why the time scale is growing so rapidly as one goes towards the glass transition. Most of these works have concentrated on the long time behavior, the alpha relaxation part. And there are several such studies have been carried out, and there have been some progress. And if somebody is interested in going into the details, there are a couple of reviews that we have written recently, and one could get a pretty good description of what has been achieved in this till now. What I'm going to talk about today is basically whether there is a length scale associated with this short time dynamics. Of course, I mean, the basic idea is that whenever a time scale is growing, there might be a growing length scale associated with it. The beta relaxation time also grows as one goes to lower and lower temperatures. The plateau becomes longer and so on and so forth. So the question that we wanted to understand is whether there is a characteristic length scale that can explain or sort of give you some understanding of what is going on there. This paper is already on archive and it's coming out in TRL. There is some unpublished stuff that also, if there is time, I'll discuss a little bit. So the first thing is what we are doing. So we are doing basically molecular dynamics simulations for 3 different glass formers. So this part actually was done some time ago, and we saw some interesting behavior. So more recently, we have carried out a similar calculation for 2 other liquids to, in some sense, check to what extent this behavior is universal. So again, no need to go into the details. It's just standard molecular dynamics simulation of a standard glass forming liquids in 3 dimensions. And the method that we use is finite-size scaling. Again, people here are all familiar with it in the sense that if there is a dominant length scale, then that should show up in the dependence of whatever you are interested in on the system size. So if you study a system with varying system size and then you see some variations, systematic variations, then one tries to relate that systematic variation to a length scale through the basic idea that the effect of the finite system size should then show up as a function of this quantity, which is system size divided by the length scale. That's the basic idea. And again, this has been used extensively, critical phenomena and so on and so forth, so let me not go into the details. So first of all, I mean, so the next few slides will tell us about the main results, which will, so first of all, I mean, so what we did was the finite size scaling of the beta relaxation time scale. So first of all, one has to define what is this beta relaxation time scale. So there we followed a prescription which was given by these people a few years ago. Basically, what one does is one looks at the mean square displacement as a function of time. And as we had seen in the case of autocorrelation function, the beta relaxation, the time scale of beta relaxation is related to this plateau that one sees here. So initially, if you do molecular dynamics, initially one finds some kind of a ballistic behavior. And then there is a plateau, which is the caging regime, and eventually the cage breaks, and the system then goes into the diffusive regime. And this plateau region, where the system is actually seeing this caging, is supposed to be the beta relaxation regime. So one basically wants to associate some kind of a time scale. And this was done, suggested by these people, that if we look at this logarithmic derivative, which is this particular set of curves, this will show a minimum which corresponds to this plateau. And the time at which this minimum occurs will be a characteristic time scale associated with the beta relaxation process. So same definition we are using. And as you can see, this time scale actually grows as one goes to lower and lower temperatures. So there is this time scale which is growing, and then we want to find out whether that can be associated with some kind of a growing length scale. And there, as I just told you, one does finite size scaling, which involves measuring this time scale as a function of both temperature and system size. So these are at different temperatures as indicated here, but we are looking at this time scale as a function of system size, and in all higher temperatures, this time scale saturates quite quickly as we increase the system size, whereas as you go to lower temperatures, one has to go to much longer systems for this time scale to actually saturate. Indicates this by itself already indicates that there has to be a growing length scale, in the sense that this will saturate when the length scale of the system becomes large compared to size of the system becomes much larger compared to the characteristic length scale, and that happens at a much smaller value of L at high temperatures as compared to low temperatures. So then one does finite size scaling as the usual way, and then one finds a characteristic length associated with these different temperatures, such that if I plot this quantity as a function of this ratio, then one gets a master curve. And the values of xi for which that master curve is obtained will tell me about how this length scale is actually growing as a function of temperature, which is shown in the next transparency. So you can see that, since of course in the glass simulation problem, there is always this issue of not being able to go to very low temperatures, because then the system cannot be equilibrated. So the temperature range is limited, but over that limited temperature range, I see a correlation length that actually goes from about this unit here is interparticle spacing, goes from about 1 interparticle spacing to about 7 or 8 interparticle spacings, which is pretty much, given the limitations of computation, what we can do today. But it definitely shows the existence of a length scale, which actually grows as one goes to lower and lower temperatures. So this is for one system, and we basically did the same calculation for 2 other model systems in 3 dimensions. And in all cases, we find similar behavior, that we find actually this scaling collapse of the relaxation time as a function of n is the number of particles in the system and temperature. And then in all these cases, we get basically over the accessible range, time scale which grows from about 1 to about maybe half an order of magnitude, etc., etc. But it certainly shows that the beta relaxation regime, which earlier was basically interpreted as this kind of caging behavior, very local in space, but that doesn't seem to be the case here, in the sense that there is a cooperativity associated with it, and this length scale that one determines the spatial extent of this cooperativity that actually increases as one goes to lower temperatures. Yeah, so that seems to be again a feature of all of the scaling function. We, of course, at this point, there is no calculation of the scaling function. This is something that we get from analyzing your data in a particular way. So theoretical reason for this peak, which is not here. So this is basically the message that we do find a growing length scale associated with this short-time relaxation. And the remaining 2 minutes, I just want to point out some analogy or some similarity or some connection between what we are finding in the beta regime to some earlier results that we had obtained for the alpha regime. And that is, I think, something which is interesting, which tries to relate the short-time behavior to the long-time behavior. And we are trying to understand that connection, and I will not have time to talk about it. But this connection is something that I just want to point out, and then I'll stop. So this is basically beta, as I said, is the short-time relaxation, whereas the alpha part is the long-time relaxation. In the alpha relaxation regime, people, including ourselves, they have found a length scale which grows, which is associated with this thing called dynamical heterogeneity. Again, dynamical heterogeneity is the spatial heterogeneity of local relaxation. And one can, by various means, one can get a length scale, tells us about associated with that spatial heterogeneity. And this is something that we had done also some time ago. The interesting thing is that the length scale that we get from the beta regime and the length scale that we had got from dynamical heterogeneity in the alpha regime, they seem to track each other very, very closely. So both these 3 systems that we have looked at, there are 2 sets of points here, red and green. One corresponds to the length scale that we get for the beta regime from this calculation, whereas the other one that we had got earlier for dynamical heterogeneity in the alpha regime. And the temperature dependence of that, of both these 2 length scales, seem to be pretty much the same. So this suggests a connection between short and long time dynamics, which we are trying to understand. I don't have time. We have some ideas as to how this connection may actually occur. And this is where this work of the present student comes into the picture, but I don't have time to go into all of that. So let's just stop here with the conclusions. Is something, again, I don't want to reiterate. Growing length scale we have found. Don't worry about it, because I have not talked about IMCT. But the same length scale governs the structure of dynamic heterogeneity, and there's some connection. This suggests a connection between short and long-time dynamics, which you're trying to understand. That is. Thank you.
Quick question.
The length scale associated with the beta relaxation not show up also in some experimental measurements of structure factor or something like
Structure factor, I don't know, because again, you basically have to then find out appropriate correlation functions. And what is the correlation function that would actually show this length scale in the beta regime is not clear to me. Because even in the alpha regime, one had to actually study very unusual correlation functions, 4-point correlation functions and so on, which would actually show signatures of this special growth of correlation. So one has to have a similar idea about what is the right quantity to look at. And structure function probably is just a 2-point function, which probably will not do it.
Are you debunking also the cage concept?
Yeah.
Now, but why not have the cage concept and say that as you go lower and lower in temperature, the cage size also increases and the length scale that you see is roughly the cage size?
That's just, rephrasing things in the sense that then one has to show that the cage is what? I mean, the particle surrounded by its neighbors. Now, if you want to include it to, so let's say, 8 interparticle spacings, then it pretty much will cover the whole system. So then the notion of cage itself becomes questionable. Yeah. So it's basically, our idea is that caging at one point and caging at some other point, these two are not independent. So the behavior of one cage is correlated with the behavior of some other cage, which is within this correlation line. But that, again, needs to be established.
Okay, we thank the speaker again for his talk. And the next speaker is Pinaki Chaudhary.